Hi folks, welcome to another video lesson here. Today we're going to be talking about applications of solving exponential and logarithmic equations. This goes with section 8.6 in your Algebra 2 textbook. Today we're going to be looking at solving real-life exponential equations and solving real-life logarithmic equations. Okay, I'm also going to add on to here that we're going to finish solving more complicated log equations. So there's some things I left out last time, the more complicated ones. So we're going to do, we're going to do one or two of those. We'll do that right at the beginning here. So we'll do that before we get into the actual applications. But I wanted to give you just a kind of dip in your toe and just an intro with the last lesson. So let's look at a more complicated logarithmic equation from what we had last time. So if you notice here, we have two log expressions, right? Log of 5x and log of x minus 1. And that's equal to 2. Excuse me, some of that is equal to 2. So last time what we had was something like log base 7 of, I don't know, something was like x, right? And then we had like log base 7 of, it was like 14 or something like that. It wasn't quite like that, right? And we said, okay, we have two logs on different sides, and we can just set the arguments. We can just say, okay, x has to equal 14 because the bases of the two logs are the same. Well, we don't have that here, right? We have this other number here, this 2, that's getting in the way of me accomplishing the task that I have there in green. So what can I do here? Well, if you notice, we're adding these two logs, right? So when we add two logs, I can condense those. This is why we spent that time condensing and also expanding logarithmic expressions. Because now I can condense this left side down into one expression, have a log base 10. And what's the operation that we do with the two arguments, the 5x and the x minus 1? Well, when it's addition of two logs, we change that into the multiplication of the two arguments. So I can write this as the single log of 5x times x minus 1. And that 5x times x minus 1, that's all inside the logarithm. And that's equal to 2. And that's really the new stuff right there. I'm going to finish up the problem, of course, but it's that condensing that's going to let me do the rest of what I'm about to do here. Okay, so I have a log equation. I'm going to solve that by changing this to exponential form. So I'm going to take my base, which of course is 10, right? Okay, so I'm just writing in base 10 for us. I'm going to say 10 to the 2 equals all this stuff in here. So 10 to the 2, I'm going to write out like this for now. And I'm going to do the step of saying, okay, this is really 5x squared minus 5x. So I've taken this log expression, this log equation, and now I change it into really what ends up being just a quadratic. So I'm going to move this 100 over to the right side. I'm going to say 0 equals 5x squared minus 5x minus 100. And now we have a nice little quadratic that we can solve by prior techniques. So I'm going to go ahead and do that. I notice here that everything is divisible by 5. So I'm going to divide both sides by 5. And I'm going to get x squared, 0 equals x squared minus x minus 20. And this is a lovely little quadratic. This is actually factorable. This is going to factor to x minus 5 times x plus 4. And hopefully this is good old fun old stuff for us here. I can split this into 2 because these multiply to get 0. You guys know how to do this, right? X equals positive 5, or we have x plus 4 could equal 0, or x could equal negative 4. So I get these two solutions of 5 and negative 4. And what I did for the last lesson and a half, just to remind you guys with exponentials and with logs, is that sometimes we get extraneous solutions. So I'm going to go ahead and check this once again. I'm going to take my 5 and my negative 4 and go all the way up to the top. I'm going to put 5 in. So I'm going to say the log of 25 plus the log of 5 minus 1 is 4. Is that equal to 2? Well, I could certainly try that in the calculator. I could just use my my log properties and say, well, this is going to be the log of 100. Does the log of 100 equal 2? Well, yeah, that means 10 to the 2 equals 100. Yeah, that checks. That works. So 5 is a completely acceptable solution here. Does negative 4 work? Well, I'm going to erase all this stuff here. Let's try negative 4. So I get the log of 5 times negative 4 is negative 20. Ooh, stop right there. I don't need to go any farther. I can't do the log of a negative value. That's exactly the problem. That's why I'm going to get an extraneous solution here. So because of this log of negative 20, I have to throw out negative 4 as a possible solution. And again, my only solution is going to be x equals 5. So you got to watch out with extraneous solutions with these log equations, excuse me. Okay, so take a moment here and try this one on your own, and I'm going to put up the answer here in about 3 seconds. Okay, so for this equation here, I get a solution of 4, and I will let you know that negative 9 ended up being extraneous. So only 4 was the solution that we had. Okay, so hopefully that worked out well for you. If not, feel free to ask about that in class, and we'll talk about it. Okay, one more. This is actually another log equation here. This one's a little bit different because, hopefully you see that our variable is down here. So a little bit new for us here. Once I change the form of this is actually going to be something that we've seen recently. So notice how this is actually nice and compact. I just have a single log on one side. I have a number on the other side. I really just need to change the form here to see what this is going to do. So I'm going to take my base to my exponent equals my argument. So x to the 2/3 equals 4. So I've taken this log equation, I change it to, well, I can't really call this exponential form anymore because this is no longer an exponential function. This has x as in the base. So I need to solve this a different way. So the way that we solved these was we raised both sides to the reciprocal power. Because think about what that raising to the 3/2 does to the 2/3. Right? If I multiply these two values here, right, 2/3 times 3/2, you want to get 1? So I need to raise both sides to the 3/2. And I get x equals 4 to the 3/2. This may or may not be something we can simplify. In this case, it is. So I'm going to go ahead and do that. But at least I isolated x. X is by itself over here, right? So I isolated x, and now I just need to simplify with 4 to the 3/2. So remember what this says. This says take the square root of 4, right? I can put a 2 out there, but we normally don't do that. So take the square root of 4 and then raise it to the 3rd power. Remember, go small before you go big. Okay. So the square root of 4 is 2, and then q cubed is going to give me 8. So my final solution I get is x equals 8. So try this one here. You're going to see it's a very similar looking problem here. Try this one here, and I'm going to put the solution up right now. So go ahead and hit pause. Okay, so the solution I get for this one is going to be 27. So how'd that go? So again, did you do x to the 4/3 equals 81? And then what did you do at this point? Well, hopefully you raised both sides to the 3/4 power. And when you do that, you take the 4th root of 81 cubits, and that should give you 27. Okay, so that was some of the preemptive stuff here before our solving. We're not going to, quite honestly, we're not going to see some of these tougher ones in the applications like this one back here, where we have these multiple logarithms that were added together. Those are really kind of standalone problems here. We're not going to see those in too many applications, if any at all. Okay. But we're definitely going to see something like our good old bank key problems that we had before. So let's take a shot at one of these. Okay, so I'm going to deposit, let's say, how about we put in $1,000 into a bank account, and I'm going to have this pay out at 5% annual interest, and I'm going to compound this monthly. And the question is, how long will it take for the balance of the account to double? So the first thing I need to do, I need to form an equation on this. So hopefully you recognize that this is a compounding problem, I'm compounding it monthly. So I'm going to grab the equation. Well, I want to have a name for it, but I'm going to grab this equation here, right? A equals P times 1 plus 1 R over N to the NT. And remember, R is our rate as a decimal. N is the number of compoundings per year. And T is the number of years. Okay, so I'm going to put into my equation the things that I know. Well, A is my future amount. I don't know what that is, at least not yet. Maybe you do. Maybe you read it pretty well and you actually know what it is. I'm starting with $1,000, and my rate is 5%, so that's 0.05 as a decimal. N is the number of compoundings per year. Well, we're doing this monthly, so that's 12 times a year. And this is going to be to the N times T, or in other words, 12 times a year times 5 years. So I'm going to put 12 times 5. You certainly can go ahead and put 60 there if you want to go ahead and put 60 there right away. But that's our basic formula that we're going to be working with. And now I just need to go ahead and modify this for the fact that my balance is actually going to double. Okay. So the fact that it's going to double, I can go ahead and change this A to 2,000, right? I'll go ahead and mark this as 2,000. And something's off here. Why did I put 5 there? That should be in the exponent. That should not have been there. That should be a big old T. So my apologies for that. You might have even picked up on that, so I apologize. Okay, so I'm going to start by unwrapping here. Okay, so what can I do? Well, it looks like the last thing that happened is this multiplying by 1,000. So I'm going to go ahead and divide everything by 1,000. And the left side I get 2. And what do we get on the right side? We get this base. You can go ahead, if you want to go ahead and put that in your calculator and get that as a number, you certainly can do that. In fact, I'm going to go ahead and do that right now. Actually, I take that back. I'm going to leave that just the way it is. I'm just going to keep unwrapping as it is. Okay, so what do we need to do next here? Well, here's my variable that I'm solving for. I want to unwrap this whole base, right? I want to get rid of that part of it. Okay, well, how do I unwrap the base part? Well, that's a logarithm, right? That's what a logarithm does. So I'm going to take the logarithm of both sides. I got to squeeze it in there. What base do I want to use? Well, I want to use this 1 plus 0.05 over 12. And it doesn't look particularly nice. I understand that. But that's what it is. That's what our base is. Again, you can get that as a decimal if you like. Just make sure that you are very precise. It's not a very nice decimal. So that's why I actually left it as a fraction. But the idea is I want to take the logarithm of the base, this 1 plus 1.05 over 12, on both sides. Okay, so what do we have here? Well, the right side is actually really easy, right? The right side, these things unwrap each other. This log and this weird base and the weird base, those things unwrap, and I just get 12t. On the left side, I have log of 2 base 1 plus 0.05 over 12. Okay, kind of weird looking base, but that's what we get. So again, I just used the logarithm as an operation to help me unwrap that exponentiation. And then I can divide by 12 here, divide all this by 12, and I'm certainly going to go to the calculator to help me evaluate this. And I'm going to use the change of base here, right? Or if you have the TI-83s, you guys can just plug that right in and get your solution that way. So I'm going to go to my calculator at this point and get an answer. And when I do that, I get approximately 13.892 years for the time that it takes to double. Something like this, that could be a reasonable amount of time. Certainly you can take that answer and plug it back into your original way up top here, right? Go all the way to the top of here and plug in this value here. And that right side should equal 2,000. So feel free to go ahead and do that if you're not quite sure how that worked out. But that certainly is not really a nice looking base to deal with. Okay. Let's look at one that's a little bit nicer. I'm going to do the same type of problem. We're going to take some money, we're going to deposit it, and I'm going to ask really the same type of question. So let's take our same $1,000, let's take our same 5%. We're going to compound this continuously this time. And I'm going to ask the same question, how long it takes for the balance of the account to double. Okay. So continuously compounded, which equation are we going to use? Well, we're going to use the PERT equation, right? The A equals P e to the RT. That's for continuously compounded. Again, you don't need to memorize these. Just like in the last quiz where I put them on the top page, you'll have full access to these equations, so no need to memorize them. Okay, so similar setup. Our money's going to double, so I'm going to start off with $2,000. Excuse me, I'm going to finish with $2,000. I'm starting with $1,000, and now this time I had e to the 0.05 as my rate times t per time. Okay, very similar operations. You're going to see this one's a lot nicer. Why is this one a lot nicer? Well, it's because of this base e, right? That base is a lot nicer to use. In fact, we even have a button to unwrap base e, don't we? We have the natural log button. So this is actually going to be real nice. So I still need to do the same basic order of operations here. I'm going to divide by 1,000 on both sides. I'm going to get 2 equals e to the 0.05 t. Okay, and again, I want to unwrap this exponentiation, this e to the part of this, right? So to unwrap that, I need to take the natural log. I'm going to take the natural log of both sides. Again, that's log base e. That's exactly how I want to unwrap this. So on the right side, well, the left side, there's nothing to do, right? This is just the natural log of 2. The left side is pretty easy as well, or pretty nice at least, because I get just that exponent, right? We spent a good amount of time talking about these properties of logs and exponents, and this is why we did it, because it ends up being really nice for us. Okay, last little bit. Let's divide both sides by this coefficient. And really, that's your answer right there. You can leave it like that, natural log of 2 over 0.05. But that might not be real nice, so I need to put that in and give me a little better answer here. So again, I'm going to go to my calculator and get us a solution. And when I do that, I get an answer of approximately 13.
Please be sure to bring your next year's schedule.
Okay, sorry about that. It's approximately 13.863 years. If you compare that to the last problem, so remember, continuously compound, that's our best result. We can't compound something better than continuously. We get a high percent, but that's not really the same stuff there. 13.863 years, and previously with the compounding monthly, we had 13.892 years. So the continuously compounded was slightly faster, wasn't it? These are close. These are sort of close enough where I could say, hey, if one of these is right, then the other one's got to be. Well, the other one's probably right, because I know that they should be really close to each other. So again, the idea here is we're using the idea of the logarithm to help us unwrap an exponential function. All right, folks, let's look at one logarithmic equation here that we're going to solve, and then we'll call it a day. All right, this is actually example 8 from your textbook. This has to do with seismology. I'm just going to read this one to you guys. And it says it's called the moment magnitude. I'm going to call it the magnitude M of an earthquake that releases energy can be modeled by this equation. So this is the equation that we get for the energy released is E, and this is the magnitude of the earthquake. Okay, so what happens if we have a magnitude of an M value, a magnitude of 9.5? That is a massive, massive, massive earthquake. Let's see how much energy actually gets released. Okay, so what I'm going to do here is, well, I'm going to put 9.5 in for M. Okay, so I get 9.5 equals 0.91 times the natural log of capital E, and then plus 1.17. So once you get to the point where you have the equation, the idea that this is an application or this is some kind of a word problem really starts to not be as important, because we're just unwrapping like we normally would if I just threw this on the board, which is pretty much what I just did here, right? Okay, so I'm going to go ahead and unwrap. Well, I want to get rid of this plus 1.17 first. So I'm going to go ahead and subtract that. Okay, and when I do that, I get 8.33 equals 0.291 times the natural log of e. And again, just keep on unwrapping. Well, I'm going to unwrap this multiplying by 0.291. So I'm going to go ahead and divide both sides by 0.291. Okay, I do that, and I get 28 and change. I get about 28.625 equals the natural log of e. Natural log of this capital E. Again, that's not the number E. A little inconvenient there, and that's why I'm writing it in capital, so you can recognize it's not the number E. Okay, so that's what I'm solving for, right? So I want to take my base. Well, what's the base when it's natural log? Well, that's the number E. So I'm going to have e to this 28.6 is going to equal the energy that's released here. So E, capital E is going to be e to the 28.625. And again, I'm going to go ahead and put that in my calculator to get a nice little number from that. And I get the energy released is about 2.703 times 10 to the 12th. That's what that little E12 means on the calculator, if you put that in your calculator. It means times 10 to the 12th. And I think the units that they give you here in the problem here are some weird units like ergs. I have no idea what that means. But our emphasis obviously is on the solving the natural log equation. So let's see, did we do the things that we set out to do? Did we solve a couple real-life exponential equations? Yep, we did that. We played around with that. And we saw some extensions from the exponential and the log equation that we solved before. And we saw a real-life log equation with the Richter scale, the seismology problem that we just finished up. So again, hopefully this was helpful, and I look forward to seeing you guys in class.